Regression is another way we can arrive at the same results seen in correlation. Let's explore linear regression in greater detail now. In linear regression, we seek to predict a behavior based on a set of inputs. For simple linear regression, we have one input, x, that serves as the independent variable, and one output, y, which serves as the dependent variable. Note that an independent variable is one that we control. We provide the numerical value. The dependent variable is determined based on the predictive relationship. Consider the example shown here. We seek to establish a predictive linear relationship between time and distance. The scatter plot to the right shows that there is some semblance of a linear behavior. If we were to place a ruler on the graph and move it about until it seems to pass through the majority of the points, this would provide us with the best fit line. Let's consider a mathematical approach with this aim in mind. The mathematical equation of a straight line for a simple linear regression is given here. Beta sub 0 is the y-intercept when x equals 0, and beta sub 1 is the slope of the line. When determining the best fit line, there will always be some random error, which is the difference between an observed value of y and the mean value of y for a given value of x. This random error is given by the epsilon in the equation. Here, y is the distance and x is time. Least squares is a statistical procedure for finding the best fitting straight line. While doing this visually can be rather straightforward, it is far from precise enough for our needs. We begin with ordered pairs, x, y. Technology is essential in performing regression calculations. The formulas shown here are meant to impress upon the necessity for technology. S sub x squared is the sum of the squares of the difference between each x and the mean value of x. S sub xy is the sum of the product of the difference between x and its mean and the difference between y and its mean. The ratio of S sub xy to S sub x squared gives us an estimate for the beta sub 1, otherwise known as the slope. The estimate for beta sub 0 is the mean of the y values minus the estimate for the slope times the mean for the x values. Once beta sub 0 and beta sub 1 have been computed, substitute their values into the equation of a line to obtain the least squared prediction equation. Using the data from our earlier example, we calculate the best fit regression line. Note that this equation determines a predicted y, given by y hat, for each x value of the data set. The best fit line can be graphed from this calculation. Notice that our visual estimate is in fact very close to the true best fit line. Again, recall that x is time and y hat is the predicted distance for our example. We can even use this model to predict a distance for any time in the range of values used to make the regression model. This would be times between 23 and 63. Entering values for x outside this range would be considered extrapolation and can be very risky. When doing regression, we should be mindful of some key points. First, be careful of rounding errors. Normally, the calculation should carry a minimum of 6 significant figures when computing sums of squares of deviations. Always plot the data points and graph the least squared line. If the line does not provide a reasonable fit to the data points, there may be calculation errors. Also be aware that the method we are using is designed for linear relationships. Clearly, Many other known relationships exist. Graphing will help us find these. Projecting a regression line outside the range of values used to build the model can be very risky. Many behaviors have piecewise functional relationships for certain intervals of input. We must examine each interval separately. Recall that there will be a difference between the actual output and the predicted output. A random error, epsilon, enters into the calculations of beta sub 0 and beta sub 1. The random errors affect the error of prediction. Consequently, the variability of the random errors, measured by sigma sub epsilon squared, plays an important role when predicting the least squared regression line. To find a valid prediction interval, we must first understand the standard error. We find the sum of squared errors. These are based on the differences between each output and its predicted counterpart squared. Our interpretation of the standard error can best be seen in the visual shown here. The standard error is the cumulative amount of the vertical deviation of each point from the best fit line. For the example earlier, the standard error is 10.94. For a 95% prediction interval, this means that at least 95% of all the values should fall between plus or minus 21.451116 of the line. A prediction interval is an estimate of an interval in which a future observation will fall with a certain probability. We assume that the observation has already been observed. We will be spending a lot of time on the idea of a confidence interval. Confidence intervals help us to localize the true population parameter. Prediction intervals help us to determine where we can expect to see the next data point sampled. The difference between a prediction interval and a confidence interval is the standard error. The standard error for a confidence interval on the mean takes into account the uncertainty due to sampling. The standard error for a prediction interval also takes this into account, but also takes into account the variability of the individuals around the predicted mean. Standard error for the prediction interval will be bigger than that for the confidence interval. As a result, prediction intervals are wider than confidence intervals. The calculations behind a prediction interval are very complex. Technology will be essential for this task. Behind every regression, there is a hypothesis test associated with our slope and intercept. The existence of a significant relationship between y and x can be tested by whether beta sub 1 is equal to 0. The null and alternative statements are given here. The test statistic is a t-distribution with n-2 degrees of freedom. Note that the test statistic is used in determining the significance of the slope within a defined level of confidence. We then arrive at a confidence interval for the slope that is based on the estimate of the slope, our standard error, and the critical t-statistic. The critical t-statistic is based on the alpha, otherwise known as 1 minus the confidence level, and the degrees of freedom, n-2. For our example, if we wish to find a 95% confidence interval for the slope, the critical statistic is 2.365. This is based on an alpha over 2 of 0.025 and a degrees of freedom of 7. Our CI for the slope will be 0.9946 to 2.4247. Therefore, we are 95% confident that the true population slope will be between 0.9946 and 2.4247. At any rate, we can clearly be very confident that the slope is significant. In other words, statistically different from zero. We could also arrive at a similar result by looking at the test statistic and comparing to the critical statistic. Using the formulas on the previous slide, we obtain a test statistic of 5.6540. Recall that our critical statistic was 2.365. If the test statistic is either greater than 2.365 or less than negative 2.365, depending on whether the slope is positive or negative, we will reject the null hypothesis. We conclude that beta sub 1 is not zero, and there is a linear relationship present. In other words, the slope is something other than zero. This was also concluded from the confidence interval calculation. Both methods affirm each other. Multiple linear regression follows a similar methodology for linear regression. However, there is more than one independent variable. As we add more variables, we add more combinations and more complexities. Higher order terms and interaction terms must also be considered under certain circumstances. Like linear regressions, multiple regressions have coefficients of determination and standard errors. Their calculation uses many of the values we have already discussed, but must also depend on the number of predictor variables, or X's.